Good afternoon. Welcome to the Research Exchange. We are coming to the end of semester, and this will be second last one. We have our very last Research Exchange next week. I am Ming Wu. I'm Chief Scientist of CITRIS, as well as a professor in electrical engineering and computer science. It is a pleasure for me to introduce today's speaker, which is my colleague in EECS. Professor Elad Alon received his PhD degree from Leland Stanford Junior University in 2006. And he joined faculty immediately after he received his PhD. He has extensive experience working with a very large number of companies even before he received his PhD, which impressed all of us where we were interviewing him. He has worked with Sun, Intel, AMD, Rambus, and Hewlett-Packard, and IBM. And his expertise is in digital, analog, and mixed signal circuit design. He has received a few prestigious awards during his short tenure here at UC Berkeley. He's received the IBM Faculty Award in 2008, 2009 Hellman Family Faculty Fund Award, and 2010, he receives a very prestigious Electrical Engineering Outstanding Teaching Award. We have always been very impressed with Professor Alon's ability to work with very innovative systems. And today he's going to tell us one of his recent research, how we can use very innovative, even nanomechanical technology to achieve power saving in electronic systems. So please welcome Professor Alon.
Great. So thank you very much, Ming, for the kind introduction. So as Ming mentioned, I'm going to tell you a little bit about sort of some of the work we've been doing on designing energy-efficient integrated circuits and systems. And I will mostly focus on some of the work that he mentioned, which is in the nanomechanical domain of things. But I thought I'd just sort of start out by maybe giving sort of a broad overview and then really motivating why it is that I think those types of designs might be particularly interesting. I should also mention, please feel free to just sort of stop and raise your hand at any time. I'd like to keep this maybe as interactive as you can, and then obviously at the end also sort of pause and ask for questions. So if any of you have ever talked to our other colleague here in EECS, Jan Rabai, you've probably heard several times now that if you look at sort of the information technology landscape, we're kind of in the middle of experiencing a pretty significant shift in terms of where the majority of the, let's say, resources and, let's say, intellectual development is really sort of focusing. So if you kind of look at what are a lot of the emerging applications that people are talking about, for example, environmental monitoring or health types of things, what's really been happening is that we've been pushing electronics out into so-called swarm around us. And what that sort of means is that, in the past we just maybe sort of used to think about our mobile devices as a way to just get to the internet. Well, you can imagine if we embedded a lot of these small sensors or devices everywhere around us, into the building, and perhaps even to our bodies, there's a lot of now sort of physical information in the rest of the world that we can be gathering and perhaps actually interfacing again through these mobile devices. So you can imagine if I've got this sort of swarm of things just gathering and collecting data all around us, clearly that's going to put also obviously big sort of burden on the so-called cloud or the core infrastructure to kind of interpret all of that information and tell us really what's going on there. Now, to actually sort of make this vision come into reality, one of the key sort of focuses of this talk is really going to be claiming that if we want to make this happen, energy efficiency in terms of how we actually build these systems is really one of the critical enablers. And the reason I say that, let's maybe sort of take a look at these different layers and why that might be the case. So in the mobile and sort of this swarm of devices, it's probably obvious that energy is a big issue simply because even on your cell phone, the battery is only so large. And really, battery scaling in terms of energy density is really very slow compared to the types of functionalities that we'd like to keep on integrating into these systems. Now, you might think that inside of the cloud where you've got a power plug and there's plenty of energy available, well, even today, according to sort of fairly recent estimates, the core or the cloud is already consuming about 8% of the US power and probably something similar in terms of the global power if you looked at all of the infrastructure and servers in the world. And that's actually been increasing very steadily over time. So although 8% maybe doesn't sound like much, keep in mind, there's a lot of other things we want to do, like grow food and, build buildings and things like that. So you probably don't want to be increasing this very much further from where it already is. So that means that even to do sort of more of the processing in the core, really energy efficiency is kind of the name of the game. Now, if you go and you talk to sort of, let's say, traditional circuit designers from maybe about, 10, 15 years ago, they'd say, okay, well, no problem. We've got our CMOS technology. It's scaling very, very nicely. Every generation we can build things something like 8x more energy efficiently than we used to be able to. Well, turns out that sort of party train has ended. Okay, so traditional scaling really has basically stopped, and this actually happened about 5 years ago or so, where we really can't actually just rely on the technology to sort of save us. We really have to sort of go and look at what are the things that we can do by design to actually make things better from an energy efficiency standpoint. Okay? So in that context, my group has been doing quite a bit of work in this general space. And if I sort of look at just what's the landscape out there in terms of what are the types of techniques we can apply to really make this happen, there's really sort of three general ideas. The first is essentially just, okay, well, let's take what we know and we love. We have our CMOS transistors. We sort of know how they behave. Let's just go and make sure we really understand what are the limits in terms of the performance of the building blocks and the energy efficiency of the building blocks that we can actually build. So that really just means sort of quantifying and really pushing the limits of currently available technologies. Okay? The other is that, as I mentioned, there's a lot of these new applications that are popping up. So things like brain-machine interfaces or these embedded sensing types of platforms, where there's actually quite a few of opportunities available for us to just go and look at those particular applications and see what we can do from a sort of circuit and system design standpoint to really optimize the energy efficiency we can get for that specific application. Because you can imagine if I take some just general purpose design and try and do any one of a number of different things, there's always going to be overhead involved in actually making that work. The last one, which is actually where I'll spend most of the talk, is, as I said before, traditional technologies really sort of aren't coming to the rescue. So that means that potentially we should actually be spending some time grabbing some of the new devices or really talking to the people developing the new devices and trying to see what's the best way for us to actually utilize these to potentially make some interesting system or application much more energy efficient. Okay? So just to kind of give you a brief idea of what some of the application and specialization looks like, as I said, most of the talk will really focus on the other side of the coin, but I just want to kind of give you a little overview of what some of the things there can do. One of the spaces that we've been spending a lot of time on is basically in building 60 gigahertz wireless links that you might actually be able to use in something like your iPhone. So this would provide you functionality to do something like about maybe 10 gigabits per second over about a 10-meter type of range. So something indoors, perhaps between all of our phones talking to each other here. You can imagine for something like very high-speed synchronizations or downloads. But if you really want to get this onto a mobile phone, then you really have to reduce the power consumption over what people are doing today by about 1 or 2 orders of magnitude. Okay, so bringing it down to about 100 milliwatts or so. So what's sort of interesting about this is that if you sort of look at what were the constraints in traditional wireless systems, for example, like your main radio that you use in your cell phone, one of the biggest constraints was really that we had very narrow bandwidth. So we had to be very, very efficient in how we use that bandwidth to actually get any reasonable throughput out of the communication. Well, in 60 gigahertz, the situation is actually kind of flipped. We've got about 7 gigahertz of bandwidth we can use to actually do our communication. But, as I said, energy is actually very, very limited. So it turns out that in that particular context, just realizing that this is what the sort of application constraints are, we can actually sort of realize that we can leverage the bandwidth rather than trying to make things very, very spectrally efficient. And by doing that, that allows us to re-architect the way we build the circuits. And in particular, if you actually build some, let's say, old-fashioned analog mixed-signal types of circuitry, you can actually make these links operate much more efficiently than they have in the past. And so I'm just giving you an example here of a particular chip that we designed, which was actually able to do all of the sort of signal processing for a 10 gigabit per second wireless link in about 25 milliwatts. Again, about an order of magnitude or two lower than what people are able to do today, following more traditional design techniques. So as I said, that's really just kind of give you an overview of the types of work that goes on in those spaces. But for today, what I really wanted to spend most of my time on was this project that I've been doing in collaboration with Sujay King Liu here at UC Berkeley, as well as Dan Markovich, who's a professor at UCLA, and Vladimir Stoyanovich at MIT, which is looking at how can we actually do digital processing in an efficient way, perhaps with using these nanomechanical relays. Okay? So before I dive into that, again, I probably need to sort of tell you, well, why would you even want to imagine replacing CMOS? CMOS has obviously been a very, very good technology for us. But as I'll try and motivate in 1 second, it's actually facing some pretty significant issues right now. So if you look starting about 5 to 10 years ago, so here I've done it since about 2000, if you look at the power supply voltage that CMOS chips have used, they've basically gotten stuck at around 1 volt. Okay? And the reason for that is that we've no longer been able to reduce the threshold of the transistors, which is kind of where they turn on and off, without actually drastically increasing the leakage current that they would burn even when they're supposed to be off. Okay? So if you actually look at some of the sort of power density predictions that people made because of this trend, people were saying that around today, we'd have chips that would be sort of operating the power density of a rocket nozzle. In other words, they'd be about, a kilowatt for one, let's say 20 millimeter by 20 millimeter chip. So I don't know about you guys. I don't want something that's, anything close to a rocket nozzle anywhere near my body. Certainly not near my head and my cell phone. So, and obviously pretty much most of the world doesn't want that either. So clearly that didn't really happen. Okay? So in fact, what really did happen is that people realized that, okay, instead of just trying to push, take one, let's say, processor core and run it as fast as we possibly can and then end up dissipating this huge amount of power, instead what you can basically do is, well, okay, if I can take my problem and basically split it up into 2 parallel processing units, then what I can do is I can essentially run each one of those units slightly slower than I did before. And that means that I can make it more energy efficient, because you can imagine anything you run slower, you can actually make more efficient. But then by actually having 2 of them operate in parallel, as long as they're both busy, then actually I've sort of made up for my overall performance or my overall throughput. Okay? So this indeed works quite well and is in fact exactly what the industry is really doing right now. And that's exactly the reason why, if you go and you buy a new laptop, they're no longer selling you how many gigahertz is that laptop. They're rather telling you how many cores are in there. And of course, this is assuming that you can actually program all these parallel things, which turns out to be a pretty big problem. But I'm going to assume that you actually can do that today. Turns out, even if we follow that methodology, unfortunately, there's another sort of looming crisis waiting for us in, let's say, maybe another 5 to 10 years or so. And that crisis has to do with the fact that if I take a CMOS transistor and I ask myself, okay, I'm not at all interested in how fast the thing needs to be. I'm only interested in how much energy does it take to do some logical operation. Turns out there's an absolute minimum number, and it's actually very easy to predict. Okay? The reason there's an absolute minimum number is that as I drop the supply voltage, the amount of power I spend sort of switching capacitors will indeed go down, but because of this leakage, as I start going slower and slower, I'm actually going to be wasting more and more energy just having my transistor sit there and leak a little bit of current out of the power supply. So if you sort of think about it, that means there's going to be some balancing point where those 2 energies balance out with each other, and that creates this absolute minimum energy that I can dissipate. Okay? Now, this is bad news because what this means is that if I keep on playing this parallelism trick, meaning I keep on running things slower and slower, but eventually I hit this absolute minimum energy, well, now game is over in terms of actually making things more efficient. Because if going slower doesn't actually make me any more efficient, then adding more processor cores just means that I'm increasing power. Okay? It doesn't mean that I can actually do more work for the same energy budget. Okay? And again, this is really fundamentally tied to the behavior of the transistor. So this isn't sort of my assumption about the circuit or something like that. This is really very much directly tied to the way the device operates. Okay? So based on that, now maybe you might start to be able to imagine why you perhaps would want to have something like a mechanical switch. Because the trick with a mechanical switch is, if I can really not have any leakage at all, meaning that when the switch is off, I'm not going to be dissipating any power whatsoever, then at least in principle, that means I can keep on taking my power supply voltage and dropping it, and therefore getting lower energy per operation. Okay? Well, from the standpoint of coming up with a switch that doesn't leak, mechanical switches are actually great. Okay? Because basically, if I have 2 pieces of metal that are far enough away from each other, there's no real way for current to flow between them. Okay? And in fact, if you don't believe me, this is an example of a particular mechanical switch that was fabricated here in the Berkeley Microlab, where you can see that essentially there's no leakage, or really it's below the noise floor of our measurement device. And then with a 1 millivolt change in the gate voltage, we can actually turn that thing on and get something like 10 orders of magnitude increase in the current that we have through there. Okay? So again, this is really exciting in the sense that this is a potential pathway for us to continue reducing the energy per operation required in our circuits. Okay? Now, I'm going to be spending most of the time here today talking about these mechanical switches, because that's where I've sort of spent most of my time and effort. But I should mention there's many other alternative devices being explored as well. And in fact, there's a new center funded by NSF that's called the Center for Energy Efficient Electronic Science, where many of these other types of switches are also being explored. So if you're interested, please do come and bug us. We've got lots of ideas on potentially how you can solve this problem. So, in terms of the particular mechanical switches that I've been working on, this is sort of a diagram of the relay that we've been playing with. So the way this thing works is basically as followed. We have this electrical gate structure that we're going to be mechanically suspending, and it's going to be made out of polysilicon germanium, and it's mechanically suspended over tungsten source, drain, and body electrodes. Okay, so the way this thing works is essentially based off of electrostatic actuation. In other words, once we apply enough voltage between this gate electrode and the body electrode, where again this gate is sort of mechanically suspended on top, then essentially we'll get enough force to collapse the structure, and then we'll be making contact from the source to the drain through this conductive piece of channel. Okay? Once we lower the voltage back down below some magic threshold point, so that now the spring restoring force from these flexures is larger than the force from holding this thing down, essentially it'll pop back off. And again, notice I just have this air gap in between the drain and that channel, which means, or the source in the channel, which means that no current can actually flow. Okay? So this is the way we would get this kind of IV characteristic, where for a very small change in the gate voltage, either you've actuated the thing or you didn't, and therefore you get this huge change in the conduction of current. Okay? So let's take a look at what it would take to actually build logic out of these kinds of switches. And the good news is that the switches actually very much mimic the way we think about CMOS transistors. Okay, so in CMOS transistors, you basically want one device that turns on when the gate is high, and another device that turns on when the gate is low. Well, it turns out we can actually do the same thing with relays, simply by changing which voltage we apply onto this body terminal. Because the thing to remember is that electrostatic attraction is ambipolar, meaning I don't care if I put a positive voltage on one side and negative on the other, versus vice versa. In both cases, I'll be applying a force to attract the two plates together. Okay? So that means that in this example, for the sort of equivalent of an NMOS, I could basically put a high on the gate, and that would apply a force. Or in the equivalent of a PMOS, I would put a low on the gate, and again, that would apply a force to turn the device on. Okay? There's one other sort of nice trick compared to what you can do with CMOS, which is, in CMOS, it turns out you can't actually build non-inverting gates. Well, with these devices, because the actuation is totally controlled by the gate to the body, you can actually build non-inverting logic circuits. Okay, so nice trick that we can potentially leverage, and you'll see that a little bit later, to actually do things that you couldn't really do in CMOS. Okay, so if you paid close attention to this sort of picture here, you can see that we're still working with pretty big dimensions. So, order 30 to 40 microns on each side for this particular device. And that's obviously quite large compared to, let's say, a state-of-the-art 32 nanometer CMOS transistor. Now, I should mention, we're building these things here in the Berkeley Microlab, so that obviously has certain limitations in terms of the minimum dimensions we can actually fabricate. And today, that's at around 2 microns or so. But it turns out you can actually follow a very similar scaling methodology that people developed in the MEMS community, but actually follow sort of simple rules that are very similar to CMOS, where essentially, as you decrease the size of the device, essentially all of the sort of parameters you care about would get better. So the voltage at which the device would turn on, that would scale linearly with the dimensions. The delay, in terms of how long it takes you to move the mechanical structure and actually turn it on, would also scale linearly with the dimensions. The energy would scale sort of cubically with the dimensions, and so on and so forth. Okay? Now, I should mention that when I take this down to 90 nanometers, this is kind of well beyond what people have actually built. So I have to make some assumptions about particularly how will surface forces scale when I get to these really small devices. But, trust me for now. I'm going to assume that that all works out. And if you don't believe me, I'll tell you a little bit later sort of how that really impacts things. Okay? So if I do this scaling on the devices that I have today, and I assume that I can get myself to something like the equivalent of a 90 nanometer device, then what I could basically do is something like the following. I can basically get a pull-in or threshold voltage of about 200 millivolts. I can get a mechanical delay of about 10 nanoseconds. And my device area is on the order of 1.25 microns squared. Okay? Now, if I go and I sort of talk to my CMOS circuit design buddies and I tell them these numbers, usually the first, the first reaction is something like, oh, that's really big and really slow. Right? Because I've got my CMOS transistor and it's like 32 nanometers by, I don't know, maybe half a micron, and it can do a few picoseconds of delay, so what the heck are you talking about here? Okay? Well, that's true, but we need to keep in mind one thing. The thing we need to keep in mind is we really aren't going to be building circuits the same way with these relays as we would with CMOS transistors. Okay? And the reason for that is pretty simple. So in CMOS, all of your delay is really set by just charging and discharging capacitors. Okay, so because of that, what you tend to do is build pretty simple gates and then cascade many of these simple gates to basically keep the amount of time it takes you to charge and discharge the capacitors relatively small. Well, in relays, your delay is totally dominated by just mechanically moving that structure. In other words, getting it from the initial off position to actually touching those two contacts. Okay? Well, what that actually means is that if I want to build something that's as fast as possible with relays, I should try and arrange it so that all of those relays move at the same time, right? In other words, what I really want to do is build big, complicated gates where I arrange all of the movement to occur, and then once that movement is done and either the relays are making contact or breaking it, then from an electrical standpoint, it's pretty quick to actually make it through that particular network, okay? So it turns out we're not the inventors of this. This was actually done back in the 1930s. You can imagine why, right? People were building things with relays back then too. And indeed, this is exactly what the issue was. And so we're basically following those same types of techniques. Okay? Now, what this means is that because I'm going to be building my circuits in a very different way, I'm really going to have to do my comparisons between what can I do with this relay technology and what can I do in a CMOS technology at the circuit level. Okay? So in particular, if I think about, let's say, the delay comparison, in CMOS, I have these sort of 4 gate stage delays, which again are set by electrical time constants. Here I'm going to have 1 mechanical delay. Okay, now, that's not to say that the relay circuit is going to be faster than the CMOS circuit. It only means that the penalty you would have thought that you were paying because of that mechanical delay is a lot lower than what you otherwise would have gotten if you designed things the wrong way. Okay? Similarly, in terms of the area, it's certainly the case that each individual relay is much larger than a CMOS transistor, but because I'm not worried about sort of driving capacitors, I'm never going to make these relays bigger than sort of the minimum size I need to get a particular operating characteristic. And in fact, as you can sort of see in this particular example, sometimes by building the circuit this particular way, I can actually build the same functionality using a lot less relays than I would have CMOS transistors. So when you look at the area, you really have to look at it at the circuit level. Okay? And so in particular, as I'll show you in a second, for many of the things that we've looked at, actually despite the devices being bigger, the overall circuit area is pretty comparable. Okay? So just to sort of give you a more detailed example, we sort of took an adder as being one specific circuit that we wanted to look at. And adders are just sort of nice in the sense that they're one of the most critical blocks you'd find in sort of a modern IC. And so everybody sort of takes an adder as being the first thing to look at and see sort of how does that stack up against CMOS. Okay? So if I wanted to build an optimized relay-based adder, again, turns out you go back, you look at sort of what people did in the 1930s, and you can actually use much of the exact same topology. So it turns out that from a logical standpoint, the best adder to build in relays is basically the good old ripple carry adder, where you literally build the hardware sort of the same way you did the addition back in grade school, where you sort of, you calculate things down at the bottom, you send a carry up to the next position, you send it up to the next position, and so on and so forth. And the advantage here is that if you'll sort of notice, all of that propagation of the carry is happening just through these sort of series paths. In other words, all of the relays are moving at the same time, and once they've made contact, electrically it doesn't take me long to actually propagate through this network. So in other words, I have a stack of these 32 relays to do that long computation, but from a delay standpoint, it's still just one mechanical delay. Okay? So if we then take that design and take that sort of projected scaled relay and see how it compares against CMOS, and when we do this comparison, we should obviously sort of take the best CMOS adder or CMOS design that we know of, and so that's indeed what we did. What you can kind of see is perhaps something that's not too surprising. Okay, so basically, in a design that has similar area, we're operating about a factor of 10 slower, because still 10 nanoseconds is slow compared to CMOS. But we're also doing about a factor of 10, if not even more than that, lower energy per operation. Okay? So it's actually pretty interesting to look at where that lower energy comes from. So a large fraction of it is just coming about because actually we have a lot less capacitance in this relay adder than we do in the CMOS adder. And the reason for that is just that our gaps are a lot bigger than the oxides in the CMOS transistor. And those gaps are air instead of oxide. Okay? So that automatically gives you a lot lower capacitance. The other thing which is quite important is we still indeed can get lower energy by lowering the power supply voltage. And I've mentioned here at least a factor of 2.4x. In fact, we can go substantially beyond that as well. That's really important because in any circuit that you build, you're going to have capacitance not just because of the relays or the devices themselves, but actually because of the wires that you need to interconnect everything with as well. Okay? So again, to zero order, perhaps not too surprising. We can indeed actually get substantially lower energy, but we're paying a little bit of a delay penalty in order to actually achieve that. Well, so it turns out, if you remember, I said that one of the most efficient ways to sort of make things be very high performance was just to take one unit and then put a bunch of them in parallel. Well, we can play that same trick with the relays. And if we do that, that'll let us actually get up to a much higher equivalent performance level. So that's fairly straightforward, but what's actually a lot more interesting is to look at what happens in terms of if we were to tweak the device a little bit, how does that impact the overall performance we get? And in particular, the device parameter that you might care the most about in this context is whether or not the contact resistance is very low. Okay? So essentially on this blue curve here, I've assumed a gold contact, which would have a low contact resistance. And for all of these red curves, I've basically assumed different versions of tungsten contacts, which would have relatively high contact resistance. And what you can kind of see just visually, there isn't a huge difference between the red and the blue curves. They're pretty close to each other in terms of sort of energy versus performance trade-off. Okay? So it turns out that's actually really, really good news from the standpoint of making these things reliable. Okay? Because you can imagine, again, usually when I sort of first tell people, oh, I'm working on mechanical switches, the first thing they say is, well, what the heck, how are you going to make this last 10 to the 15 cycles or something like that so that I can actually build a computer out of it? Well, turns out, because of the fact that I'm really dominated by that mechanical delay, changing the resistance doesn't really impact me all that much. So what I can actually do is go and intentionally increase the resistance at those contacts just to try and improve the reliability. And from a sort of intuitive standpoint, the reason that helps is that if you have a large resistance, the amount of power you dissipate when you make that contact is going to be substantially lower. That means that the temperature you're going to have of that contact will also be substantially lower. And so the chance of you essentially welding that contact during the sort of switching event gets much, much smaller. Okay? So in fact, by using these relatively hard contacts, we've actually been able to build relays that lasted up to about 65 billion cycles or so. And I should mention, we stopped at 65 billion not because the thing stopped working, but because the students sort of got bored and wanted to go home because it took a while. Okay? But even sort of theoretically, we've actually been able to sort of develop a model that tells us that if we can actually scale the voltages down to around 1 volt or so, we really could get to this sort of 10 to the 15 cycles level, which is something that you'd need to basically run a relay chip for about 10 years at a reasonable operating frequency. Okay, so from a reliability standpoint, we think actually we've got some reasonable answers in terms of what is it going to take to make this really work. So once we kind of figured these things out, we really wanted to go and see, can we actually put some of these circuits together and really demonstrate that at least the basic functionalities we're interested in will actually work. So again, in collaboration with our device colleagues, Sujay King Liu in particular, we built this test chip here in the Berkeley Micro Lab, where I won't really walk through the details, but we actually were able to demonstrate quite a few of the sort of basic types of operations you might be interested in to build up a digital processor. So you can see we have like a full adder over here. This is using that cell that I mentioned earlier. We even have something like a little memory structure, in this case a DRAM. We also had some things like oscillators and flip-flops. So basically we're actually able to demonstrate that, at least in principle, the basic functionality for a lot of these types of circuits is indeed achievable. Now, having said that, we've obviously still got a long way to go. Maybe if you didn't notice over here, the time axis was like seconds. This is not because the devices were really that slow. This was just us sort of turning knobs in the lab. But nonetheless, our devices are still quite large compared to what we'd like them to be actually be competitive with a CMOS technology. So really the next step is, how do we sort of go and take these basic principles and really get them down into something that would be sort of competitive with CMOS dimensions today? And of course, also would be sufficiently reliable, have sufficiently high yield, and so on and so forth. So we've definitely still got a long way to go on that front. But as a sort of first step, we've actually been working with Sematech to go and basically move from our kind of equivalent of a 1 or 2 micron technology down to something that's more like a 1/4 micron technology. So this is a chip that we taped out about 3 or 4 months ago. We're hoping to get some of these devices back for kind of the first round fairly soon. And we're hoping we'll be able to show that we can at least take this first step in terms of the scaling, so that future scaling, obviously we want that intermediate step to convince ourselves that we can really keep going and make this happen. Okay? So we'll see if that really works or not. That's really work in progress. But you can kind of imagine, if I started this whole thing out by saying that in CMOS there was this limit that I said that we were eventually going to hit. And any new technology that I might propose, I better be careful to really think about what is the limit I might hit in that technology as well. Because if I don't think about that, I could sort of spend a lot of time investing and developing and getting this thing to kind of work, and then just realize after the fact that the limits in terms of energy for that new technology are not that much different than what I would have gotten with a CMOS transistor. So what I wanted to just briefly do now is convince you that we actually have a pretty good idea of what the limit for relay technology would be as well. Okay? So it turns out that from an energy standpoint, the limit in terms of what you can do with relays is really just set by the fact that once you've made that relay turn on, and basically you're making contact between those two pieces of metal, there are always forces that tend to once two things touch each other, there's always forces that tend to want to make them stick together. Okay? So from the standpoint of the relay, what I have to do is, in order to make this thing work, I have to ensure that I've stored enough spring energy to be able to pull back off once I've made that contact. Right? Because if I get stuck down, then I don't have a working switch anymore. Okay? So what that really asks, or the question that really begs is, how big is the surface force? And how will it scale as we drop the dimensions of the relays? So we've done some preliminary experiments, and it looks like, at least initially, from where we are now, as we reduce the area of those contacts, that will indeed reduce the amount of force that's being applied at those contacts, which means we could keep on reducing the energy. Okay? So if we actually sort of extract out what that energy number would be, it turns out to be something like 5 microjoules per meter squared. Okay? If I was able to really get to my 90 nanometer device, which maybe would have a 90 nanometer by 90 nanometer contact, that would imply something like 0.04 attojoules per relay sort of switching event. Okay? Now, you look at this number and initially it actually sounds really great. It turns out it's actually pretty close to sort of thermodynamic limits. But anytime you see something that good, you again sort of have to ask yourself, well, okay, is that really what's going to happen, or is something else going to sort of crop up and really become the main issue? And turns out there is indeed sort of a pretty important sort of thing to keep in mind, which is that ultimately at the end of the day, if you really want to be making contact, that means you sort of have to form a bond between one metal atom and another metal atom. Okay? Because that's sort of the minimum contact I could have, right? Well, each one of those bonds has a certain energy associated with it. And so the more of those bonds I make, the more energy that it's going to take me to basically rip those things back apart and break that bond. It turns out that energy is at about 0.2 attojoules per bond. Now, the good news is if we built a device with something like 4 or 5 bonds, that would mean we could actually build a relay that would be dissipating on the order of single attojoules of energy per operation, which nicely enough is indeed still about a factor of 10 to 100, lower than what you could actually do with even scaled CMOS devices. So that says, it looks like we still do actually have some room to actually improve over what people can do today. Okay? So with that, I just wanted to sort of briefly wrap up and maybe open it up for questions. And so what I hope to kind of tell you a little bit about, at least from the beginning, was just that, again, if we look at the sort of emerging applications that are out there, it should be pretty clear that energy efficiency is one of the critical issues we need to solve in terms of actually making these swarm types of things become a reality. The second point was really that I hope to convince you that from the standpoint of what we as integrated circuit and system designers can do is really have a pretty big impact on how energy efficient things can be implemented. And there's really sort of three ways that we can do that. The first is just by sort of quantifying and, again, pushing the capabilities of currently available technologies, like CMOS transistors. The second is really looking at just what are the applications that are out there, and then trying to co-optimize our actual implementation with that specific application. And then the final is really looking at what are the devices that are coming out there and understanding how can we really leverage those devices in the best way to actually implement some interesting building block or perhaps even complete system. And that's obviously where I spent most of the time in talking about our work on the mechanical relays. So just as one sort of like final closing thought, integrated circuit design is sort of a field that's actually been around for a little while, and starting to become, I think, a little bit more mature. But at the same time, I think this is actually a very exciting time because of the fact that really things are now changing in a pretty dramatic way. So from the application side, there's really a lot of new things that are popping up, which really gives us the opportunity to sort of look at a lot of different disciplines and understand how can we really tailor the things that we build to make them the most energy efficient in this different application space. On the other hand, as I said, because CMOS is really running into these roadblocks, there's now a lot of work on alternative devices. In fact, not even just for sort of computing applications, but even just to support a lot of these sort of, let's say, sensing or other modalities that are now becoming increasingly interesting. So that also means that as circuit designers, we really have the opportunity to sort of go and look at those devices and see what's the best way for us to actually make use of them. So with that, I'd like to thank, in particular, my students and postdocs and collaborators, and thank you all for your attention.
Thank you. So do we have any questions from the audience? Okay.
So I guess we were just giving you the microphone.
So here.
Well, if you have energy, why do you want to save it? I mean, why? If you have enough?
Well, okay. So as I was mentioning earlier, if you sort of look at the projected trend lines in terms of how much energy we're using just on electronics today, we're already at about 8 to 10% of the global energy consumption. Right? So if you just think about from the standpoint of greenhouse gas and all of these other, let's say, energy-related issues, if we keep on increasing that number, then pretty soon we're just going to be paying or we're going to be using all of our carbon credits just to sort of run your computer, which I think most people probably don't want to be doing.
Well, since you have two different types of circuit elements here that are sort of orders of magnitude apart at some things, have you looked at hybrid circuits, which would be reconfigurable gate arrays that then are optimized to CMOS to do some particular function?
It's a great question. So we've done a little bit of work in that space, although it turns out that the trick is that really once you sort of hit this fundamental limit in terms of leakage with the CMOS, if I put anything there that's CMOS, then I'm kind of stuck with that limit. So we've really been mostly focusing on kind of doing this blanket replacement, but you can imagine there's going to be still a lot of, let's say, things like analog and interfaces where you'd still want to be using this traditional CMOS technology because it'd just be too hard to actually, or there wouldn't be any benefit in doing it with a relay type of thing. So that's a great question.
So could you use the relays as sleep transistors?
Okay, great. So you absolutely can. We've actually done some studies on whether or not that's really worthwhile. And it turns out that's very highly application dependent. And in fact, it's really sort of very cost dependent. Because if all you care about is sort of making a sleep device, you can imagine I could build a pretty specialized CMOS transistor that's really, really low leakage and get pretty similar benefits. So the question would really end up being, what is the sort of cost trade-off between building that special CMOS device versus using this relay? Now, there may indeed be applications where you really absolutely need zero leakage. And from that standpoint, a relay would be very attractive. But to be honest, I haven't found that application yet. So if you know one, please let me know.
Hey, I don't understand how the ripple carry adder is the best architecture. Shouldn't you have to wait for the carry to get from one bit to the next?
Yeah, so this is not to say that it doesn't take time for you electrically to get the carry from here to here. It's only saying that that amount of time is very, very small in comparison to what it would have taken me if I actually had to basically take the signal, feed it to the gate of another relay, and wait for that relay to actually mechanically move. Okay, so you can kind of think of it as if it takes me, let's say, 10 picoseconds or 20 picoseconds or even 100 picoseconds to get through each one of these paths, but it takes me 10 nanoseconds to go this way, I'd much rather pay the 100 picoseconds.
Any other questions here? You have a mic, yes.
So Elad, you also been preaching it's very difficult to design a logic without gain. And what's your take on the pure mechanical circuits?
Okay. Well, so that's a good question. So there are structures in which you can get sort of the equivalent of mechanical gain, right? And in fact, even in something like this, you can imagine I can make something that has a sharp transition. So when I say gain, that means I always mean sort of large signal gain. In other words, over some range of voltage or over some range of whatever the control variable is, I really can actually find a noise margin. So I was actually thinking about this a little bit the other day. I'm not sure if there's an immediate benefit in going to all mechanical logic in the sense of propagating mechanical variables might actually be sort of more costly than just moving the electrons around. But in principle, I don't think there's any reason why it can't work.
Okay, well, I think we're out of questions here. So I just want to thank you again for a great talk.
Great,
Thanks
thank
so
you.
much.